And what I want to do quickly now is show a class of arguments for obtaining lower bounds on classes of algorithms. And this class of arguments is going to be, is called the information theory lower bound arguments. Now I'm going to go over this very quickly because information theory lower bounds are taught in a fair amount of detail in the undergraduate courses. We don't talk about the adversary arguments typically, and so I'm going to spend more time on that. But I want to quickly talk about information theory lower bounds and maybe in some more abstraction than the way you might have seen this in the undergraduate courses. So actually, let me take a show of hands, by the way. How many people had ever seen this algorithm before? So a third. And how many people have seen information theory lower bounds? Or you may not know it by that name. Probably more than the number who've seen this one, but you perhaps don't know it. So I want to, basically I'm focusing on a set of algorithms that work in the following way. They do some computation which does not involve branching. And then they branch. They make some binary branching, some comparison. And then depending on which way they branched, they do some more computations. So we're not going to need to know, really, what kind of computations they do, what are their primitive operations. All we need to know is that when they branch, we'll assume it's a binary branch. They may be comparing two numbers. I don't know what it is they're doing specifically to decide which way to branch, but then having branched one way or the other, they then do some other computation which doesn't involve branching, okay? So alternate between some straight line code, well, actually straight line with iteration, and some branching. It's really easiest in this business to think about the algorithm written in assembly language. Okay, you don't. It's a lot easier if you just see the thing written out in very, very primitive form, so that there's an explicit branch when you branch. There's an iteration that's permitted, but it has to be a fixed number of times. If it involves some parameter that's being tested, then that's really an implicit branch in there. And that's why it's easiest just to see it in gross detail. Straight line, unwrapped if it's iteration a constant number of times, and then possibly some branching. And so in fact, we usually represent such an algorithm or such a program as a tree. Binary tree. Where each node is where some straight line code is, and finally some branch operation. And so it branches one of two ways, but I'll write up both possibilities. And then if it branched this way, it does some straight line code, and finally does some comparison, or sorry, some operation which allows it to branch one of two ways. And over here we have the same sort of thing. And this tree of possible behaviors, this is a tree of possible behaviors of the algorithm, is not necessarily balanced. It's binary, but it could be very imbalanced. It could look like that and be very misshapen. But ultimately, along every particular path, the algorithm terminates, and it has some particular output. Okay, so every leaf is associated with some output. All right, everybody got the viewpoint? We're just considering a class of algorithms that each of which can be represented in such a way. And this is fairly general. For example, the sorting algorithms that we know of, merge sort, insertion sort, heap sort, whatever your favorite sorting algorithms are, they can all be represented like this. I mean, what's typically happening at a node, doing some work, maybe it's swapping some elements, I don't know what else it's doing, but ultimately it makes a comparison between two elements and then branches. Well, I'll rig those algorithms so they branch in two possible ways. Sometimes you get an equality in there, but that's just, we can deal with that later. Yeah?
Why doesn't the tree have to be binary? Couldn't there be more than two possible paths?
Well, as I was just saying, I'm rigging those algorithms so that they're binary. And if you have an algorithm which can make a ternary decision, okay, then it'll just be a tree, let's say, with 3 edges coming out of it. And you'll see after a while that it's not going to matter as long as this is a finite number of branches. But binary is an okay assumption, even if it's comparing two numbers to see if they're greater, less than, or equal. If you do as I was suggesting, and think of this at the assembly language level, that's really, I mean, I don't know if that's a primitive operation in most machines. I think of it as more than one. So you can test whether it's strictly greater, test whether it's strictly less. I don't know. Anyway, I can always express this binary. Okay. Did that answer your question? Yeah. Okay. But to be more general, just carry along in the analysis. This is just some finite number. But it does have to be finite. It cannot depend on the size of the input. All right, so we have a whole class of algorithms which fit into this framework. Now, when it comes to sorting, there may be some algorithms that don't fit into that framework. Okay, you can try to think of one if you want. Anybody got one? Those of you who've seen this before should think of one. Yes?
Maybe in general, recursive algorithms?
No, recursion is just a way of disguising. Recursion is just a way of making you nuts. I mean, ultimately, that recursion is, if you were to unwrap it, for some fixed input, and you unwrap the recursion, it's ultimately just some straight line code followed by a decision followed by straight line codes, depending on what you do. The recursion is just a programming device. But the algorithm itself fits into this framework, even though the expression of the algorithm is recursive. Now, there is an answer that people who've seen this movie before should be tempted to answer. It would be wrong, but they should be tempted to say it. Now, who's brave enough to do that? Hmm? Are you saying something that's not like that? A sorting algorithm that doesn't fit into this framework.
Is there a bucket sort, for example?
Maybe bucket sort. Okay. What's the other one that people are tempted to say?
Sorting algorithm doesn't use comparison.
Well, sorting algorithm, the suggested answer was sorting algorithm not based on comparison, but as long as the outcomes are binary, whatever branching is done, it doesn't have to be a comparison of two numbers, say. Now, what's usually treated as special, as separate, is radix sort. But I want to point out that radix sort fits in here perfectly well, because I didn't say what was happening in this branching. Usually what the branching is in terms of sorting algorithms is you're looking at two complete numbers and seeing whether one is bigger or less than the other. And then radix sort violates that because you're actually looking at bits. But radix sort fits into this because when you look at a bit, in radix sort, you're doing a binary, you're branching on the basis of what you saw. You saw that bit was either 0 or that bit was 1, and you're still branching based on what you see. So in this more general framework, even radix sort fits in here as well. Okay, so we've got a whole class of algorithms described this way. All the favorite algorithms that we know of for sorting fit into this framework. And now I can get the lower bound on the number of operations that any algorithm has to do. Any algorithm that fits into here, I can get that lower bound by just asking a few questions. So question 1 is, and now I'm specializing this for sorting. Okay, so we are now dealing with the sorting question for illustration. And then I'll show it to you. Is the question, did I talk about it in 122?
The class, if we've seen it before, it seems
Those
like
of you who have
nobody-
taken 122, did I talk about this in 122?
Yes.
A lot.
Yeah.
Okay, but we did it more specialized, and now I'm doing it more generally. I'm doing it in a way that radix sort fits into that framework. What I don't like about the treatment of this typically is this argument is typically made in terms of algorithms which compare two numbers, sorting algorithms that compare two numbers all at once, and then they treat radix sort as if it's some kind of weird cousin, and then they have to come up with ad hoc explanations for why this sort of applies to radix sort, which is really weird for those of you who think radix sort runs in linear time. Okay, we'll get into that in a minute. But this argument for lower bound is going to apply to radix sort as well. Okay, so what is, okay, for sorting n numbers, what is the minimum number of leaves any such tree must have? Let me explain the framework again. You have a specific algorithm in your hand that comes from this class of algorithms. And for a specific value of n, there is a tree which explains, which lays out in gross detail how that algorithm behaves. Okay? And now I'm asking, as a function of n, as a function of the number of numbers, of the size of the input, what is the minimum number of leaves that such a tree must have? Any such tree that comes from that class must have. I hear n log n, I hear n, I hear n factorial. That's a pretty big spread there.
But if you have unsorted input numbers, then any permutation of those numbers can be a valid output. So we have to have at least as many leaves as possible permutations of n numbers, which is n factorial.
Right. The answer, as was suggested here, is we have to have one leaf at least for every possible output, every possible answer. In this case of sorting n numbers, they're n factorial permutations of those numbers. There's got to be n factorial possible answers. I mean, when a sorted list is output, you can line it up. You can take a look at the unsorted list, and which is given in some memory locations. Let's say they're consecutive, and you can look at the sorted list, and you can see what the permutation was between the unsorted order and the sorted order. All right, and if the algorithm is always right, if the algorithm has full generality, every possible permutation has got to the algorithm must have the ability to come up with any of those particular permutations. So the algorithm has to have at least n factorial different leaves because the algorithm has to be able to output essentially n factorial different answers. Or another way of seeing this is the algorithm has to have at least n factorial different behaviors when it operates. Okay? Each time it comes down to a leaf, it's finally telling you what the sorted order was. And if it has less than n factorial leaves, there's some particular sorted order that it can't tell you about. okay, because they're n factorial sorted orders. Okay, so the answer to this question is n factorial. Got to have at least n factorial leaves. All right? Now this is true for any one of those algorithms that's in that class. You take an algorithm from that class, you fix n for the moment of, for clarity, you look at the tree, and we're asking now as a function of n, if you look at those trees as a function of, well actually for any fixed n, it has to have n factorial leaves at least. Second question, if a binary tree has n factorial, well, let's just make it more general, k leaves, what is its height at least? It could be very misshapen binary tree, but we're saying that ultimately you get down to k leaves. Is it possible that for k equals 1,000,000, it only has depth 6? Yeah, the answer here is log base 2 of k. And I can upper bracket or whatever. I mean, every level, it's at most doubling the number of nodes at that level. If it's at most doubling it, once we get down to the bottom, to the farthest leaf from the root, the maximum possible leaves we have there is 2 to the depth, 2 raised to the depth power. That means that if there are k leaves, the depth has got to at least be log base 2 of k. Okay? So any one of those trees, let's call it a sorting tree, has to have at least depth log base 2 of n factorial, because it's got at least n factorial leaves. Okay? Now, we're out of time, but I'll just tell you, and you can do this, look it up in the book. Log base 2 of n factorial is a function which grows as theta of n log n. It's not too hard to see that, if you know the answer. Yeah, the upper and the lower bound are both. Anyway, look in the book for this particular mathematical manipulation. But let me just remind you what we've proven. We've proven that for any algorithm that fits into that framework, in worst case, it must do a number of operations. It must have a depth, at least omega of n log n. And therefore, in worst case, the number of operations it does must grow at least as omega of n log n. See you next time.